So, it's time to look at solving equations in algebra, which we've done some of before, but now the situation is going to change slightly. If I asked you to solve this, you might either say A is 3, because you know that 3 add 4 makes 7, or you might say that I subtract 4 from both sides to eliminate the plus 4 by doing the inverse operation. Either method is fine. So what about this equation? Can you solve this equation? Well, I think you have, but you're concerned about your answer. So, what did you get for A? A could have been 2 and B 3. Well done if you said that. A could have been 1 and B would have then been 4. A could have been 5 and B 0. Now, this has lots of solutions. In fact, A could have been 1.23 and B 3.77. A could have been root 2 and B could have been 5 minus root 2. Now I can sit here all day and come up with new ways to solve this equation. In fact, it has infinitely many solutions. Now, as a quick side note for some of you who will have done some work on graphs already, let's imagine this said x plus y equals 5. Well, I could rearrange that to get this, which would be a straight line graph going through 5 with a gradient of -1. Now, the reason there are infinitely many solutions is there are infinitely many points on the line that exist that follow the rule. If you haven't seen graphing yet, don't worry about this. Just focus on the fact that whatever you do and pick an A, there's always a B value you can pair with it to make 5. So, we have a problem. An equation with 2 variables isn't solvable to get a specific answer. But an equation with 1 variable is. Okay, well, let's look at another situation, shall we? What if I told you that A plus B was 5, but A plus 2 lots of B was 6? Can you tell me what A or B is? Okay, I'll give you a clue if you haven't got there yet. It's B, I think you can work out from here. Okay, look up here. We did the same operation to both sides of the equation. So let's look at that in this particular case and see what's been done to both sides of the equation. Well, this side has had an extra b added to it. Gone from one lot of b to two lots of b. Over here, we've had 1 added. So you might tell me then that b, each b, is worth 1. Now, you've just come across a really important concept here. Having a second equation with 2 variables in allowed us to be able to solve it. What we did was we took a pair of equations and we solved them simultaneously. We solved them together. We used the information in one to help us work out the other. Let's try it again and see if we can spot another pattern. So I'm going to go for a plus b equals 4 this time. Now some of you might be thinking negatives and change the numbers and fractions and what happens if it's different. We'll cover all of those things, but we're going to build up slowly. So let's look at this one. Okay. So, let's look at our red arrows and describe the same thing here. Well, what's been added from here to here? We've seen 2b be added. And on the other side, we've seen 14. So, our conclusion then is that 2 lots of b is worth 14. Which means we can then work out that each b is worth 7. So, what we've established here in part 1, before we go and look at the formal methods for solving, which allow us to use this rule in its proper way, is one equation with one unknown, we can do that. One equation with 2 unknowns can't be solved. 2 equations with 2 unknowns we can solve by looking at what's different from one line to the next. So in part 2 of simultaneous equations, we're going to formalise this method, and then we'll be able to find both a and b in a whole range of scenarios.